Now let's welcome Cathie Yoon. So we're really excited to have her. She's a software engineer working on applied cryptography at Chain. She received her bachelor's and master's degrees in computer science from MIT with a focus on computer systems engineering. Cathie will be talking about Chain's transaction virtual machine. Here you go.
Thank you so much. Hello. I want to say thanks to Monica. That was a really great talk and actually lays a lot of the groundwork for what I'm going to be talking about, especially with regards to smart contracts, which I will just call smart contracts for my talk, but I agree with everything she had to say about the definition of it. So once again, I'm Cathie. I'm a software engineer at Chain, and some of the previous talks talked about the really cool protocol engineering work being done in the blockchain space, and I think I'm really lucky that I get to work somewhere where we get to think about how do we want to represent transactions on a blockchain, what does a blockchain mean to us, how are we doing consensus here, big questions like that. And so I got to work on this really cool project called TxVM that was basically answering the question of how do we want to represent transactions on a blockchain. So some background on what Chain does, and this is relevant because what Chain does as a company shapes what we want our blockchain to look like. So Chain builds ledger services for financial institutions, and this ranges from big companies such as NASDAQ and Visa all the way down to small fintech startups. And when I say we build ledger services, you can think of it almost as we offer a ledger as a service product. So we support their financial transactions on our blockchain. So our underlying technology is the blockchain, and the reasons for this are many, because of the cryptographic signing capabilities, because of immutability, because of the potential for supporting confidential assets, because of smart contracts. All of these reasons are good reasons to have your transactions be represented on a blockchain. And for our specific customer base, we want to support very high transaction volumes, which means high throughput, very low latency. We want to have multiple different kinds of issued assets, not just one asset per blockchain. And we want to support smart contracts. And we like to think that this is also the same design goals as other blockchain projects have, and this is why we open source a lot of the projects that we have, because we think that the research we're doing should be and could be reused in other blockchain projects. And one thing that I didn't list up there, but that is very, very important for financial companies, is that the blockchain is secure. And this has many different meanings, but in this context, we want to be able to guarantee to these companies that when you make a transaction or when you create a smart contract, it does exactly what you think it does, and that you can double check that and guarantee that. And that later, you don't actually find out that it does something entirely different and steal all your funds or something like that. So these are the design principles that we have in mind going into creating a blockchain, or rather a transaction representation on a blockchain. So when we started, we looked at the existing approaches. There's sort of two big existing approaches, or two classes of approaches out there. The Bitcoin approach and the Ethereum approach, or what I like to think of instead as the deterministic approach and the imperative approach. So these two approaches exist, and we looked at them, and neither of them really fit what we needed for our transaction model. And I'll talk a little bit more about why. So this is a Bitcoin transaction. This hopefully looks a little familiar. You have the header, you have the inputs and the outputs, and you need to guarantee that your inputs, the sum total of your inputs, equals the sum total of your outputs. So hopefully that is something that we covered earlier today. And for each output, you have a little script that is attached to it. And the output script basically checks, like, do you have the permission to make this output yes or no? It can answer yes or no depending on whatever it's allowed to check. One thing to note is that a Bitcoin transaction is declarative. What that means is that it declares the change to the blockchain state that will happen as a result of adding this transaction. So to be more specific, it declares that the inputs are going to be removed from the UTXO set, and the outputs are going to be added to the UTXO set. So this is a declaration. And you know that if you were to add a transaction, you know exactly the effect it will have on the UTXO set. You don't have to guess, well, if the UTXO set has this certain thing, then maybe this will happen, or maybe this other thing will happen. I'm not sure. This is a very clear declaration of the effects on the UTXO set. And this makes it really easy to reason about what's going to happen as a result of the transaction. And so we really like this model because it's simple, it's really secure, it's really easy to reason about. The only drawback to this model for us is that the script is not actually able to support a very expressive language. And what I mean by this is that the script isn't able to do introspection because each script is bound to each output. And so the script can't look at other outputs, it can't look at other parts of the transaction, and as a result, it can't support more complex smart contracts, such as make this transaction valid or make this output valid if there's another item in this transaction that does this certain thing. You can't do something like that because of the non-introspection of the script. So we looked to another model, the Ethereum model, which does support smart contracts that are very flexible and very powerful. And the Ethereum model is imperative. And what I mean by that is that the code executes, and the execution of the code actually affects the global state in a way that you can't tell ahead of time. So in this diagram, this is an Ethereum contract, or this is an Ethereum transaction, and it has this code that executes. And when you execute the code, what you're actually doing is you're calling functions in these globally deployed global contracts. And these contracts can do all kinds of things. They can call other contracts, they can update other contracts, they can delete other contracts, they could delete themselves. It's, you can do anything. And so you don't actually know what effect the transaction is going to have on this global state until you actually add this add this transaction to the blockchain and it gets run. So this is cool because you're basically, you can do whatever you want, but it is not very safe or easy to reason about because when you write the contract, when you write the transaction, you can have a certain state in your global contract, but then when it actually gets added to the blockchain a long time later, the global state can be totally different, and it can be really hard to reason about all of these possible global states. And this could be simple if you're just talking about one global contract that does one thing and has two possible states. But if you have contracts that interoperate, they depend on each other, if one library all the way down the line gets deleted, how would that affect you? It's really hard to reason about these things. And it's actually the result of this is a lot of security vulnerabilities that we've seen in the Ethereum smart contract space. And so Chain, working with companies like Visa and NASDAQ, this is not exactly the kind of thing that Visa is excited to integrate with. They're like, we don't want to have a smart contract that potentially is going to steal a bunch of our funds. No, thank you. So this was not exactly a model that we were excited about using, although we thought that we could learn a lot from the design of this, especially the part where it allows us to have very versatile smart contracts. So what we did is we created our own transaction representation, which we called TxVM, which is short for the Transaction Virtual Machine. So we wanted it to be deterministic and isolated like Bitcoin, so you can know exactly this effect that a transaction would have on the global state. But we wanted it to have the expressive language of the Ethereum virtual machine. And we also wanted it to execute in a safe environment like the Bitcoin transaction model. So these were our goals. And the way that we did this, from a very high level perspective, is that we had a representation where the transaction is the program. You execute the contract, and that actually determines your value flow and provides all of your validation. So this sort of sounds like Ethereum so far, but the execution of this program actually creates a transaction log, and this transaction log gets applied to the UTXO set. So hopefully this sounds a little bit actually like the deterministic Bitcoin model. So intuitively we have the expressiveness of Ethereum that creates a deterministic transaction log that allows us to have the static deterministic properties of the Bitcoin model. So hopefully this sounds pretty cool so far, but it's a very vague overview. So I'm going to jump into a little more detail of how this works. So in TxVM, Well, another thing to mention is that in TxVM, we actually introduced this new concept where we have first-class values and contracts as part of the type system. And so anyone who's studied sort of like programming language design, you know about first-class objects as having being objects that you can apply special rules to or special limitations to. And so we use that same design principles when it came to designing our language. So values and contracts actually have constrained operations that preserve what we call the law of conservation. So you cannot accidentally create more value or accidentally destroy value the same way you cannot accidentally create contracts or destroy contracts, or maliciously. And the values and contracts must be cleared from the VM by the end of execution, which means you can't run a transaction and accidentally forget about executing a contract or accidentally forget about a value. And this means that you can't bypass any contracts that must be executed in order to make a transaction valid. So I'm seeing like a few confused looks. So I'm going to give an example. For instance, if you wanted to bind a transaction to a certain contract, and this contract says you can only spend the output of this transaction if you can fulfill this contract. And for example, if this contract is like you must satisfy this like multi-checksig program, then if you did not have the second rule, then you could potentially say, well, I'm going to extract the value that is attached to this contract and I'm going to spend this value, but I'm going to forget about this contract on the stack. And by forgetting about this contract, I'm going to just not fulfill all of the rules that it requires me to fulfill. That would be really bad, and that's why the second rule is really important. So one example, I'm going to give an example of a walkthrough of why it's really cool that we introduce these first-class values. So pretend you have an example ride-sharing transaction, and in this ride-sharing transaction, you have a rider that pays $15, or is it 5? I can't. 10? The rider pays $10. And then you want to split this $10 into some payment to the driver and some payment to the company. So ideally, it is $15. No, it is $10. I'm not sure anymore. Sorry. So ideally, you want to split this amount into two different amounts. Okay, it's $15, sorry. And you want to pay $10 to the driver and pay $5 to the company. So this makes sense. And what you can do is you add this input, the $15 input, to the VM, and then you run the split operation, and this splits it into $10 and $5. And then you create a contract that binds the $10 to the driver and sends it to the driver, and binds the $5 to the company and sends it to the company when this is done. And keep in mind the two rules. The first rule, that operations preserve this law of conservation. You can't create or destroy value. And the second rule, that all objects must be cleared from the VM by the end. So this example transaction met both of these rules. However, what I mentioned earlier is that we're creating a language and a representation for a transaction that makes it really hard for people to mess up. Even if you really wanted to, you could not make an invalid transaction, or you cannot make a transaction that steals money or loses money, because that's something that's really important to us and our values of security, and also something that's really important to our customers who want to have guarantees about the security of their transactions and smart contracts. So pretend, for an instance, that you have a software engineer who's just like really exhausted. It's like a Friday afternoon, they haven't gotten enough sleep, and they're writing a smart contract, and they just forgot about like rounding for division, or like what to do for decimals for division. So pretend that we have a $5 ride now, and this and maybe the tests only tested $15 rides, but now we have a $5 ride, and now you're splitting it into 2/3 of the ride goes to the driver, and 1/3 goes to the company. So you take this $5, you divide it by 3, and so 1/3 of it, aka $1, goes to the company, and then you multiply that by 2, and $2 of it goes to the driver. So now you took this $5 value, you split it into $1 and $2. That sounds not great. And this actually violates the law of conservation, that we implemented in our rules for values. So you physically could not do this. You could not call an operation that achieves this split of $5 into $1 and $2. It's just not possible. So our language actually keeps you from making this mess up. So what if the engineer is still like really sleep deprived and like, oh, this isn't possible, but I'm just going to take this $5 and split it into $1, $2, $1, $1, and another $1, or $2, $1, and $2, because they still haven't figured out what to do for the remaining rounding. So what happens with these three values? Maybe the $2 goes to the driver, and the $1 goes to the company, and the engineer forgets what to do with the last little bit. So this actually would result in an invalid transaction because all objects must be cleared from the VM. And so when you leave this $2 value at the very end on the VM, the transaction is not finished running, and therefore it can't be valid. And so it's not physically possible for someone to mess up and make this transaction a valid transaction. But what you could do, if you really didn't want to fix this rounding issue, is you could have the first value go to the driver, maybe a second value go to the company, and then the last bit maybe could be a tip to the driver. And if you did that, then the last one would also be output from the VM, and that would satisfy both of the rules because all of the objects would be cleared from the VM, and you didn't violate the law of conservation, and as such, this could be a valid transaction. So hopefully that was a cool walkthrough of how we designed the smart contract language to be extremely secure and extremely hard to mess up. And I think this is actually something that's really important when we're thinking about design going forward for any blockchain protocol, because as much as we would like to think that we're perfect, there will always be mess ups, and we want to design a system that is robust against human error, instead of assuming that humans are always going to get it completely right the first time, especially when it comes to something that is immutable, so you cannot reverse it once you've made an error, except for maybe with a hard fork, but that's kind of crazy. So this is really important in our design principles. So some of the TxVM internals that we have are the stacks, the transaction log, a run limit, and the actual code that operates. And the VM rules, just to reiterate, is that you must have empty stacks. So everything must be off of the stack by the end, that the transaction has to be finalized, that your run limit is not exceeded, and that you can't fail the execution. And the blockchain updates are all of the effects that are stored in the transaction log. And so you remove the inputs in the transaction log, and you apply the outputs in the transaction log. So I'm going to just click through really quickly an example of TxVM transaction. And if you want to go into more detail, you can look at our white paper and our blog post and our documentation for more detail. But this is an example transaction. You take in a $10 value. You take in a $10 value from the UTXO set, so Alice is $10. You take in maybe another input, Alice is $5. You run some operations. In this case, you merge the $10 and $5. And then you create a contract, such as a contract binding a value to Carol, and you call the contract with the $15 value, which outputs that amount to Carol. And then you finalize the transaction, and then you use the finalized transaction ID to make signatures with Alice's private key, and then you call the contract still in the stack, and that allows you to finalize or complete the whole transaction. And as you can see on the very right-hand side, as we were going, we were populating the transaction log with all of the resulting inputs and outputs of the transaction. And so now if this transaction is valid, then we can go apply these changes to the transaction log, aka we will tell the transaction log we're going to remove Alice's $10 input and remove Alice's $5 input, and we're going to add Carol's $15 UTXO output. So this is generally how it works. As a recap, we declared some inputs, we managed the value flow, we declared new outputs, we froze the transaction log so you couldn't edit the log after it was done, and then we cleared the remaining contracts by adding signatures. And these are contracts in this diagram. I didn't go into too much detail because of limited time, but you can read more about that. online. This is the instruction set. These are all of the operations that you're allowed to do in the TxVM virtual machine. And as you can, if you have experience with other like smart contract languages, this is actually very small. You're not able to do many operations, but the operations that we decided to include in this operation set are very powerful and are very specific to the values and the contracts that we decided to support. So as a conclusion, TxVM is a new model for blockchain transactions that hopefully increases security and readability and all of the, basically all of the goals that we had for our customers to support a very high throughput representation for transactions on the blockchain. It borrows the good parts from Bitcoin and Ethereum, namely the determinism from Bitcoin and the expressiveness of the Ethereum language. It has very powerful abstractions, which are first-class values, and contracts, which have their own rules applied to them to maintain safety of the transactions. And we kept safety and understandability of the language very high priority when designing it. And we actually open sourced TxVM, and we have a white paper, and you can view those here at the Chain blog and at the Chain open source repo. So just to recap, this is a project that I worked on at Chain, and it's been really cool working at Chain because we get to work on projects like these where we ask ourselves, what do we want out of blockchain for our business, and how can we design that? And this is something that I worked on and that we open sourced recently. And actually, I'm currently working on a new project about confidential assets on the blockchain, which is also super exciting and also is something that we have open sourced and written up a write-up for. And you can read about all of those really cool research projects on our website and our blog. Cool, so thanks for listening. Does anyone have any questions?
Thank you. I was wondering how TxVM transactions take into account any fees or anything, because this obviously seems very easy when you're saying $15, divvy it up into like $5 and $10, but when we're dealing with so many decimals or characters, how does TxVM address that? And clearing it. Obviously, I see everything needs to be cleared, so when I think of fees, I think that I need to have the exact amount in there or something if I'm utilizing it, so any clarity on that would be great.
Yeah, for sure. So the examples that I gave were all pretty abstracted, and obviously I use whole numbers, but you can use any amount of decimal places that we support in. I think it's like U64. So that is not an issue with the decimal places. And with fees, if you wanted to introduce some requirement that in order for a transaction to be valid, it had to have some amount of fee output to a certain pub key, then you could just introduce that rule, and then anyone who is validating a contract would say, well, I'm only going to validate this transaction, for instance, if it has this exact fee output or this % fee output. And that's a pretty straightforward thing to check for, because anyone who's validating transactions would already be running the transactions, and this would just be one additional rule that they could check for, the same way that you could check for like a pay-to-pub pub key script. Maybe Monica?
This is super cool. I love anything that limits what Solidity can shove into the EVM. I noticed that you included a jump statement in your transactions, and I was wondering why that choice, given that your focus seems to be on security and not letting people fuck up, and yet Turing completeness and letting people junk around is almost never useful and almost always a situation in which somebody is going to accidentally have an infinite loop and run out of gas.
Gotcha. So your eyesight is very good with your glasses on. So yes, we included the jump statement because, and this was actually something that we were debating, because we think that it actually results in a much greater expanse of what you're able to do with a smart contract. For instance, I guess an example would be like if this branch is fulfilled, then go this way, otherwise do this other branch. So that is a plus, and the minus being having an infinite loop, for example. And we defend against that by having a very solid run limit cap, where every operation you do costs a certain amount, and once you hit a certain cap, then it's no longer a valid transaction. So that's how we get around that. But with regards to just like generally people messing up, we thought that introducing the jump, but having the safeguards of all of the limitations of what you're allowed to do with the first class values and contracts actually negates all of the ways that you could mess up, because even if you mess up for the jump statement, you're still limited by the law of conservation for how much you can mess up the values and the contract. So that was sort of our debate and how we ended up resolving it and how we feel that it's still a very secure system.